So now that we've looked at the order of operations and the three algebraic laws, we can now approach the topic of rearranging equations. Now so far we've only really looked at equations that have numbers, not variables. And this has been really useful to us because it allows us to check that the various manipulations we've been applying to the expressions do in fact leave the overall value of the expression unchanged. However, in reality, it is far more likely that we're going to encounter expressions and equations which use variables. Now, a variable in algebra is not that much different to a variable in programming. It is a container that can hold a value. For example, in the equation 4 plus x is equal to 6, x is a variable. It is a container that can hold any value. However, for the equation to be true, we know that x must hold the value to it, must hold a very specific value because 4 plus 2 is equal to 6. 2 is the only value that we can add to 4 to get 6. So what we've actually done, albeit mentally, is to rearrange the equation 4 plus x equals 6 in order to solve for the value of x. And that is precisely the reason for rearranging equations. We're rearranging them in order to solve for the value of a particular variable. So why is this useful to us in computer graphics and programming? Well, there are many scenarios in which you might encounter equations. Perhaps you're trying to procedurally model something based on a geometric equation. Perhaps you're generating an animation based on physical laws and are using equations from a physics textbook. Perhaps you're writing a shader and using yet more laws of physics as they relate to the interaction of light with materials. There are countless scenarios in computer graphics and programming in general where an equation might state a rule or a set of rules that govern something that you're trying to work with. However, the way the equation is written, whether researched through textbooks or online, or perhaps you've derived this equation yourself, it might not immediately give you the variable that you're interested in finding, and thus you may need to rearrange that equation in order to get the variable that you're finding in terms of everything else that you already know. So for example, let us take one of the basic physics equations. A very simple physics equation states that speed is equal to distance divided by time. Now this equation has three variables: speed, distance, and time. Given values for the distance and time variable, it's very easy to calculate speed. For example, let's say that we have travelled a distance of 180 miles. So distance is equal to 180 miles. And we have travelled that distance in 3 hours. So time is equal to 3 hours. I'd like to work out how fast we were going. So we can simply put these values into the variables in the equation, and that'll give us the value of speed. Speed is equal to 180 miles divided by 3 hours, which is equal to 60 miles over hours, more commonly written as 60 miles per hour. So you can see, given distance, given time, it's very easy to calculate speed. However, let's speculate that that's not the problem that we're trying to solve using this equation. What if we had a slightly different problem? What if we knew that we'd been travelling at a constant speed of 70 miles an hour? And that for that constant speed that we've been travelling, we have actually travelled a total distance of 168 miles. So distance is equal to 168 miles. What I'd like to know is how long have we been travelling at 70 miles an hour in order to have travelled 168 miles? And currently, we don't have an equation that gives us that answer. We need to know time in terms of speed and distance. What we can do, therefore, is rearrange this equation, rearrange speed equals distance divided by time, in order to give us time in terms of speed and distance. In other words, we can rearrange the equation to solve for time. Now, there are only a few simple rules that we actually need to remember when we are rearranging equations. The first is that we must do the same to both sides. We can't, when rearranging an equation, modify the result of the equation. For example, as I scroll down, if we had x equal to 2, I can't add a number just to the left-hand side of the equation. For example, I can't say x plus 2 equals 2. And we can see that the reason I can't do this is that if x equals 2, then x plus 2 does not equal 2. We have changed the value, if you will, of the variables in the equation, and we're not allowed to do that. Similarly, we cannot just add a value to the right-hand side of the equation. I can't say x is equal to 2 plus 2, and I will rewrite that x as an algebraic x, just so that we don't confuse it with a multiplication sign. So x is equal to 2 plus 2. Again, we can see that that's wrong, because that's saying that x is equal to 4. And if x is equal to 4, well, x can't possibly be equal to 2 and equal to 4. We've changed the value of the variables in our equation. So again, we can't just add a value to the right-hand side. What we can do, however, is add a number to both sides of the equation. That's perfectly fine. So if we had x and we added 2 to it, then we need to make sure that we add 2 to the right-hand side of the equation as well. We can see that therefore what we're saying is x plus 2 is equal to 4. We know that x should also equal 2 if we put 2 into x. We're saying that 2 plus 2 equals 4. We know that's true. We know that 2 plus 2 does in fact give us 4. Therefore, by adding 2 to both sides of the equation, we have not changed the value of x. So there is a really important rule there, and that is, we must, if we do anything to the equation, we must do the exact same thing to both sides of the equation. And when we're rearranging equations, all we're really doing is simply performing a number of operations, ensuring that we perform those operations to both sides of the equation in order to not change the value of the variables in that equation. And we perform those operations in order to try and isolate a variable, in order to get a variable on its own in terms of all the other variables on the other side of the equation. And we can combine this idea with our knowledge of the algebraic laws and our knowledge of the order of operations in order to rearrange these equations for whatever purpose we might need. Now, it is quickly worth noting that some equations are incredibly complex, and thus they can't actually be solved in this analytical manner. They can't be solved by just manually rearranging things. However, for all equations that can be solved analytically, no matter how complex those equations, the method is always the same. You always do the same to both sides. So returning to our speed equation, as I scroll up, here we go, speed equals distance divided by time. What can we do to get time on its own, to get time equal to some combination of speed and distance? Well, firstly, I don't really like the fact that time is currently underneath that divide there. That makes it really hard to separate it from distance. We need to get rid of the divide. And another way of saying that we want to get rid of the divide is to say that we want to cancel the divide. And here's another set of rules that apply to rearranging equations. Multiplication cancels division, and vice versa, just as addition cancels subtraction, and vice versa. So again, these are the other rules to remember when rearranging equations, and that is, multiplication cancels division, division cancels multiplication, addition cancels subtraction, subtraction cancels addition. And we can see this if we step away from our speed equation for a second and take a look at a very, very simple example. If we have 10 and we divide 10 by 2, we get 5. If we then multiply that by 2, we get 10 again. Thus, 10 divided by 2 times 2 is equal to 10. The divide by 2 and the times 2 cancel each other out. Now, you often see mathematicians write this in the following way, and this is my preferred way of writing this, is to say that 10 divided by 2 times 2, that these cancel each other out, giving us just the 10 there on its own. So in the same way as dividing and multiplying, cancelling like that, let's say we had 10 and we multiplied by 2. That gives us 20. If we then divide it by 2, that gives us 10 again. So if we multiply and then divide, they both cancel each other out. The important thing to note here is that they only cancel each other out because they're applied one after another to the same number or variable. And that's where our order of operations and algebraic laws comes in. If we were to have, let's say, 10 divided by 2 plus 3 times 2, we can't cancel the divide by 2 and the multiply by 2 because the multiply is not multiplying the result of 10 divided by 2. It's simply multiplying the 3. We can see that because of our order of operations. We work out the divide, we work out the multiply, and once we have those, we add them together. So in this case, they don't cancel each other out. However, instead, if we were to have this equation, 10 divided by 2 multiplied by 3 multiplied by 2, we could use the commutative law to write this as 10 divided by 2 times 3. I've simply switched these two guys over. And now we can see that the divide by 2 and the multiply by 2 are applied one after each other to the same number, to the 10. Therefore, in this case, they do cancel each other out. So in this case, it's equal to 10 times 3, which is equal to 30. So multiplication cancels division and vice versa, just as addition cancels subtraction and vice versa. Keep that in mind when you're rearranging equations. So I'm going to go back to our speed equation, but this whiteboard's getting a little cluttered, so I'm going to bring up a new whiteboard and let's rewrite our speed equation. So speed is equal to distance divided by time. So remembering we must do the same to both sides, and that multiplication cancels division, and division cancels multiplication, addition cancels subtraction, subtraction cancels addition. What can we do to cancel the division by time? Well, multiplication cancels division, so let's multiply by time. But remember, we must do this to both sides of the equation, so simply we're going to multiply both sides of the equation by time. So speed multiplied by time is equal to distance divided by time multiplied by time. You'll notice because we've multiplied both sides of the equation by the same value, we have not changed the value of those variables. We also notice that our divide and our multiply cancel because, again, it's the whole point. That's why we multiply by time, was to cancel out that division, giving us speed multiplied by time equals distance. So we're making some progress here, but we're not quite done yet. If we were trying to find the distance travelled for a given speed and a given time, then we'd have our equation. However, we want to find the time travelled for a given speed and distance. We need to isolate time. We need to get that on its own. It's currently being multiplied by speed. Recall that division cancels multiplication, so let's divide both sides of the equation by speed. So I'm going to take speed multiplied by time and divide by speed, and that is the same as distance divided by speed. We said that division cancels multiplication, so we know these two cancel each other out. And that leaves us with time is equal to distance over speed. Fantastic. So now we do have an equation rearranged to solve for time. We can plug in our value for distance, plug in our value for speed, and get the time that it took to travel that distance at that speed. And if you recall back to when I first set the problem, I said that our distance was equal to 168 miles and that our speed was 70 miles per hour. Well, 168 divided by 70 gives us 2.4 hours. So it takes 2.4 hours traveling at 70 miles an hour to travel 168 miles. And that's the basics of rearranging equations. It's really simple once you get the hang of it. So I now want to actually start building the complexity here, looking at examples that start bringing in some of the other rules that we've seen over the previous videos. So I'm going to scroll down just a little. There we go. And let's write a new equation. So I'm going to say that y is equal to, I don't know, open parentheses 3 plus x, close parentheses, multiplied by, open parentheses 4 plus z, close parentheses. And I want to find, again, x in terms of y and z, so we need to try and isolate that x variable. We need to try and rearrange the equation to solve for x. And we need to really get rid of some of these things on the right-hand side of the equation, if possible, to get x on its own. Now, when rearranging, there's actually a simple guideline that we can follow to make things a lot easier for us. In most cases, we need to use our order of operations to find the last operation that's being applied to the side of the equation that we're trying to simplify. So in this case, we're trying to simplify this side of the equation to get x on its own. So we want to find the last operation that's being applied and then cancel out that operation. Now, this isn't a concrete rule, but it's a guideline that I personally find works in the vast majority of cases. So we must be careful here in this particular example and remember that because of our order of operations and because we have parentheses, that they are going to take precedence over all of our other operations. Therefore, we must treat our 3 plus x as a single item and our 4 plus z as a single item, and then we multiply those two items, if you will, together. Thus, that multiplication here in the center is the last operation that is applied. Excuse me. That's the last operation that's applied. That means that's the operation we need to cancel. So to cancel a multiplication, we need to divide. What are we going to divide by? Well, I want to divide by the side of the multiplication that doesn't contain x. I want to try and get this guy on his own. That means I really want to cancel out this side of our multiplication, so I'm going to divide by 4 plus z. So y is equal to, my apologies, let's make sure we actually divide both sides of the equation, otherwise we'd be breaking rule number 1, and that would not be good. So y divided by 4 plus z is equal to 3 plus x multiplied by 4 plus z all over 4 plus z, and we said that division cancels multiplication, so these two guys cancel out. So y over 4 plus z is equal to 3 plus x. Now you notice, because it would have 3 plus x in parentheses, but the parentheses are around the entirety of the right-hand side of the equation, they don't actually affect the meaning of that equation. They don't affect how it will be evaluated, so we can simply drop those parentheses. Now, you can also notice I've been writing a lot of these steps in where I write the division on both sides of the equation, and I then cancel the division out basically by drawing through it like so. You're going to notice in subsequent videos I'm going to start missing out that middle step. So let's say in this example I was dividing both sides by 4 plus z. Instead of seeing me divide both sides by 4 plus z and then cancel through a multiplication, what you're going to see me doing in subsequent videos is to basically just take this 4 plus z and only divide by it on the left-hand side in this case, and just get rid of it on the right-hand side. And that's just due to the personal way that I see these equations when I'm rearranging them. I don't see this equation in my head as dividing by both sides and that cancels out part of the equation. What I see is that I'm grabbing this 4 plus z and I want to move it to the other side of the equation. And in order to move it, because we're multiplying by it, I divide by that part of the equation. So in my mind, rather than basically doing this to both sides and cancelling things out, I find it a lot easier, a lot clearer to think about grabbing parts of the equations and moving them from one side to the other, and then the fact that if you're multiplying on one side, if you want to move it to the other side, you need to divide by it. It all comes from the idea of doing it to the same, doing the same to both sides and those cancelling out. But in my mind, it's clearer to move things from side to side. It's just a more visual way of approaching it, and that's how I have sort of personally developed to solve equations. Now, that's just my personal way of working things out. In this video I am going to continue showing all of the workings, and I do encourage when you're first starting out to put all your workings in just so that you don't miss a step or make any simple mistakes. But if you get more comfortable with rearranging equations, I'd advise just trying, just to see if it works for you as well as it works for me. Just try thinking about grabbing parts of the equation and moving them to the other side, as opposed to thinking about it in terms of doing the same to both sides and then cancelling things out. Just for me, I find that makes the process a lot quicker and it makes it a lot easier to understand what's going on. Just as I get a sideline there for a second. So back to our equation, we now have 3 plus x on its own. So I just need one last step in order to isolate our x. We can see from the commutative law that we could switch the 3 plus x around. So y over 4 plus z is equal to x plus 3. And you'll notice I haven't added anything, I haven't removed anything from either side of the equation, so there's nothing that needs to be done to the left-hand side. All I have simply done is switched the terms of that add operation on the right-hand side. And this was just to make it a little clearer for what I'm going to do next, because I want to get rid of that 3 from the right-hand side. We're adding the 3, therefore we need to cancel it by subtracting 3 from both sides of the equation. So y over 4 plus z minus 3 is equal to x plus 3 minus 3. These guys cancel each other out. And there we have it. There is the solution for x. X, as I write this now, just switching the sides around, so x is equal to y over 4 plus z minus 3. Now you'll notice where I subtracted 3 from the left-hand side, because of the order of operations, I am indeed subtracting from the entire left-hand side. We work out that division first, and then we subtract 3 from it. That is important. We need to make sure that when we're doing performing an operation to both sides, that we're actually performing that to the entirety of both sides of the equation. So we do need to make sure that if we're subtracting 3 from the right-hand side, we subtract 3 from the entirety of the left-hand side. The order of operations in this case have made it such that we didn't need to put parentheses in to clarify that. So there we go, we've solved for x in this case. It's quite a simple equation. I'd like, before we move on to any questions, I'd actually like to look at a more complicated example, and again we're going to be solving to find x. So I'm running out of whiteboard space, I'm going to bring up a new layer. There we go, fantastic. And let's look at a slightly more complicated example. So y is equal to, let's say, z plus 3, and I want to multiply that by x, as I make sure I write an algebraic x times 3 in parentheses all squared, divided by 2 times z, and then adding the result, or adding to the result of that division, y minus 5. So again, we've got z plus 3, we're evaluating that, we're evaluating everything in these big parentheses, multiplying them together to get y. Inside the big parentheses, we're taking x times 3 and squaring it, dividing the result of that by 2 times z, and finally adding to that y minus 5. Now, for those of you that are quite new to this equation might look very intimidating. And actually, it's very simple to solve to find x. All we need to do is tackle this equation in small chunks, one part at a time, and we'll see when we do that it's quite easy to rearrange this equation and isolate x. So recalling our guideline, we need to find the last operation being applied to the right-hand side, because x is on the right-hand side. It's the right-hand side that we want to start reducing to try and get x on its own. So we need to find our last operation. And we know, using our order of operations, that parentheses are going to be evaluated first, then exponents, multiplication and division, and finally addition and subtraction. Because parentheses are being evaluated first, this part of the equation gets evaluated, then all of this part of the equation gets evaluated, and finally that multiplication gets evaluated. So it's the multiplication that is the last part of the right-hand side of this equation to be evaluated. And we've seen that if we've got a multiplication, to cancel that multiplication, we need to divide. And we've seen really how easy this can be. If I was to write this slightly differently, if I was to write this as y equals a multiplied by b, where we know that a is this parentheses and b is the parentheses over here on the right, if we wanted to cancel part of this equation, let's say we want to cancel the a part of the equation because b contains our x, thus to get x a little bit more on its own, we're going to cancel our z plus 3, our a part of the equation. We simply divide both sides by a, so y over a equals a times b over a. They cancel, so y over a is equal to b. We can extend that idea to this much larger concept where we have those parentheses. I'm just going to draw a line so we can keep our working up here. I can say y divided by z plus 3 is equal to z plus 3 multiplied by, I'm not going to write it all in, but our big parentheses here, all over z plus 3. Those two guys cancel, and that leaves just the big parentheses on its own. So we've already seen how we deal with those kind of situations. They're very simple, so even though it looks complicated, we just need to find the last operation, it's a multiplication, and then cancel that operation out with a divide. Which term of the multiplication do we divide by? Well, we want to divide in such a way that we get x a little bit more on its own, so we divide by z plus 3. So if I was to rewrite this now, I'm going to scroll down just a bit. So y divided by z plus 3 is equal to, and we've got those big parentheses, x multiplied by 3 all squared over 2 times z, and then we're adding to that y minus 5. Now you notice these big parentheses over here on the right hand side don't change the meaning of our equation because they are containing the entire right hand side of the equation, so we can actually get rid of these. And already our equation is looking a little bit more simple to solve. So again, we need to find the last operation that's being applied, remembering PEMDAS, parentheses, exponents, multiplication, division, addition, subtraction. Well, we can see here we do have some parentheses, so these are all going to get treated as single items. We're then going to square, because square is an exponent, this parenthesis. We're then going to divide, and then we're going to take the result of that and add y minus 5 to it. That means the last operation that we're applying is that addition, and that means that's what we need to cancel. Now, which side of the addition do we want to cancel? Again, we have x over here on the left. We want to try and get x on its own. We want to get rid of this part on the right. So I'm going to subtract y minus 5 from both sides of the equation. So y divided by z plus 3 minus y minus 5 is equal to x times 3 all squared over 2 times z plus, as I squeeze this in, y minus 5 minus y minus 5. We've seen these two guys cancel. Thus, we're dealing with y over z plus 3 minus y minus 5 is equal to x times 3 squared over 2 times z. So again, we can analyze our equation. Again, we're trying to isolate x over here. So we're finding the last operation that's taking place on the right-hand side of the equation. We know that that now is this division because it's parentheses first, then our exponent, then our division. To cancel the division, we are going to multiply. What are we going to multiply by? 2 times z. Now we need to be careful here because we must multiply both sides of the equation by 2 times z, and we must multiply the entirety of both sides of the equation by 2 times z. So over here on the left, we're going to take y over z plus 3 minus y minus 5, and we need to take the entirety of this and multiply it by 2 times z. And that is going to be equal to x times 3 squared over 2 times z multiplied by 2 times z. We've seen these two cancel each other out. So that means that y over z plus 3 minus y minus 5, all of that evaluated and multiplied by 2 times z, that's equal to x times 3 squared. So we're making some real progress here. So again, we're trying to isolate x, we're trying to get x on its own, but we can't break apart that x multiplied by 3 because the entire result of that is being squared. So we need to cancel out the square first. How do we cancel a square? We take the square root. So if we're going to take the square root of the right-hand side, we must make sure we take the square root of the entire left-hand side. And I'm also going to note that this square root is going to be a plus or minus square root. We've discussed that in an earlier video, why that is the case. You don't actually need to note that it's going to be a plus or minus. Just by the fact that it's a square root is enough to tell us that it's plus or minus. But if you find that it helps prevent mistakes at any point, then it's just worth noting. I personally find that it helps me to always remember that there are two solutions to a root, rather than just taking the positive solution and perhaps forgetting that there are two solutions. So I personally always write it in. So we're going to take the root of the entire left-hand side of the equation. So I'm going to leave myself some space to write the root sign in. And this is y over z plus 3 minus y minus 5 multiplied by 2 times z. And I want to take the square root of all of this, so I make sure I get all of this inside the square root, and not forgetting that this is indeed plus or minus the square root, and that is equal to x multiplied by 3. You'll notice I cancelled the square here, and then because we have parentheses around x times 3, but they don't change the result of the equation, we can get rid of those. So we are really, really close now to having our final result. To get x on its own, we simply need to divide both sides of the equation by 3. So I'm just going to shift this over a little bit to give me some more room. So y divided by z plus 3 minus y minus 5, all multiplied by 2 times z. We've got square root of all of that, plus or minus. We have to take the entirety of that and divide it by 3, and that is equal to x times 3 over 3. We know that you cancel. I am going to erase this just so I don't have to write this again. Fantastic. And that gives us the value of x. So even though right back at the start, as I scroll up, we saw that y is equal to z plus 3 times the entire result of x times 3 all squared over 2 times z plus y minus 5. It's like, whoa, that's a scary equation. That's really complicated. We see if we actually work through this step by step, take each little piece at a time, break bits off of this right-hand side of the equation, move them over to the left, you notice that step by step, each step is actually very simple. Each step it's very clear to see what we need to do. And eventually we end up with x here on its own on the right hand side. We end up with an equation on the left hand side that, though it looks kind of complicated, if we're trying to find x, we can pretty much guarantee that we know the values for y and z in most of these more simple cases of equations where we're trying to solve for a single variable. If we know the values of y and z, we can simply plug those into the left hand side. They'll just then become numbers. Then it's quite easy to evaluate that equation and get the value, and in this case values, because we mustn't forget there's a plus and a minus here, so there's two different versions, values for x. So there you have it, a much more complex example, and yet it still just used those same basic rules. We must do the same to both sides, and we have the various methods for cancelling different operations. Our order of operations allows us to work out which operation is being applied last, which in most cases allows us to determine which parts of the equation we can break off, break apart, and simplify. And without even thinking about it, our three algebraic laws came into play in order to make sure we don't change the value of the equation while we're manipulating it at any point. So if you're just starting to rearrange equations for the first time, it can often be kind of hard to see how you can break the equation apart, which operations you can cancel in which order, etc. So do start out with more basic examples, get some practice in until you get the hang of things. But once you do start picking it up, once you do start getting the hang of things, you'll find that you'll be able to tackle increasingly complicated equations, making use of all those earlier experiences, and in the end, even equations that are far more complicated than the one I just showed here are going to be simple and quick to solve. So I do actually want to look at one last example before I set some questions. Now this is going to be quite a simple example, but it demonstrates one last point that I'd like to make in this particular video. Again, we're going to be rearranging an equation to find x, and again I'm going to need a new whiteboard because we are running out of whiteboard space. So let me bring up a new layer. Fantastic. And the equation that we're going to be rearranging to find x is going to be x divided by y is equal to 2 times x over y plus z times 5. So hopefully you can see the point that I'm trying to make with this equation. Notice, up until this point, we've just had a single instance of x, if you will, and it's been on one side of our equation. Here we've got an x on the left and an x on the right. So how do we go about solving these types of equations? Well, when we encounter this type of situation, we need to gather all of the variables we're trying to solve for on one side of the equation. And obviously that means we need to gather all of the other variables on the other side of the equation. So in this example, we could approach this in two ways. Either we're going to try and move the x that we've got here on the left over to the right, and all of the other variables, our y and z, over to the left. Or we're going to try and take our x that's on the right here and move him over to the left and try and get this y over to the right. I think that in this case I'm going to approach it by trying to move our x over to the left, because we can very quickly move the y over to the right, and then all we've got to try and really do is get this x on its own so that we can move it back over. So I think it should be fairly simple. So I'm going to try and move that x from the right to the left. Now what I need to do first is really get the x on the left on its own, just so that we start out with only an x over here on the left, and then we can try and bring our other x over. It'll make things a little easier. You also see the way I've actually designed this particular equation. Things work out really nicely for us if we do get this x on its own, and you'll see that pretty much in the next step. So how do we get this x on its own? Well, we're dividing it by y. How do we cancel out a y? We multiply by y because we're dividing it. So therefore we need to multiply both sides of the equation by y. So as I try and squeeze this in, x divided by y multiplied by y is equal to 2 multiplied by x divided by y plus z times 5. Now recall, we must do this to the entirety of our right hand side, so I'm going to put that in parentheses so that we know that we are multiplying everything, and we're multiplying that by y. These two y's over here cancel out, so we can see that x is equal to all of 2 times x over y plus z times 5 multiplied by y. So we need to try and bring this other x variable out over to the left. And before now, what we've done is we've looked for, okay, what's the last operation that's being applied here on the right, and we cancel that. But if we look for our last operation, you're going to notice, well, we've got parentheses. Okay, so this gets treated as a whole. So that means we're taking this and we're multiplying it by y. That multiplication, this guy right here, is our last operation. But we don't want to cancel that multiplication, because if we do, we end up right back here where we started. We've only just put that multiplication in. This poses a bit of a challenge, doesn't it? Well, actually, there's something else that we can do here. Rather than necessarily just cancelling out that multiplication, what if we were to use our distributive law to expand these parentheses? So what if we were to expand this multiplication that we've just put in? Then we may have a different equation over on the right, and then we may be able to simplify two things from there. So let us expand our equation. So we've got x is equal to, so I need to multiply all of this guy by y and add it to all of this guy multiplied by y. So I'm going to take 2 multiplied by x divided by y multiplied by y, and I'm going to add it to z. That is a z, not a 2. My handwriting is kind of sloppy. I do apologize again for that. Z multiplied by 5 multiplied by y. So we can see from this, actually things have got a little simpler. There are actually 2 observations that we can make here. The first is that we can see we're dividing by y and then we're multiplying by y. So these 2 guys cancel each other out. That makes our life very easy because we're now getting x more and more isolated over here. The other thing that we can see is that the order in which we multiply z, 5, and y, because of our associative law, the order doesn't actually matter, and that means we can simply get rid of these parentheses around the z times 5, because it doesn't matter if we multiply z and 5 and then multiply it by y, or whether we multiplied 5 by y and then by z, the order is the same, and because of our order of operations, we will evaluate all 3 of these before our addition. So I'm going to simplify this down, so x is equal to 2 times x, and we're going to add to that z times 5 times y. And because of our order of operations, just to make things a little clearer, I said again, we're going to obviously deal with our multiplications before our addition. So that means we're really treating z times 5 times y as one item. So I'm going to put that in parentheses there just so that we can see that indeed our last operation is this add. So now we're trying to get x on its own over here, or rather we're trying to get the x over here so that we can bring it over here on the left, so that we're left with x's on the left and y and z on the right. So we can see, well, we've got an addition as our last operation. How do we cancel addition? We subtract. But what do I want to subtract? I don't want to subtract z times 5 times y, because that will leave me with x over here and an x on the right as well, and then that hasn't really helped us bring the x's together. What I want to do is somehow move this guy over to the left. So I'm going to write an extra step in just so things are nice and clear, and that is using our commutative law, I'm going to switch these 2 guys around. So x is equal to, that is a z. Wow, my handwriting is terrible, sorry guys. Z times 5 times y plus 2 times x. So there's our commutative law. And now I can subtract 2 times x to cancel that out. So x minus 2 times x is equal to z times 5 times y. And we know that we would add 2 times x and subtract it, they'd cancel out. So I'm just going to leave this in its simplified form. So x minus 2 times x is equal to z times 5 times y. Well, if I've got x and I take 2x away from that, what's that going to give me? Well, that's going to give me minus x. If I have one of them and I take 2 away, that gives me minus 1. So minus x is equal to 7, wow, z times 5 times y. It's late and my handwriting's really throwing me. Z times 5 times y. We just have one last thing that we need to simplify, that negative x. We need to get rid of the negative. How do we get rid of the negative? We're going to multiply both sides by minus 1, because negative x times minus 1 gives us positive x. If we do that to the right hand side as well, then we know that we're not changing the overall value of our equation. So minus x times minus 1 is equal to z times 5 times y times minus 1. X is equal to z times 5 times y times minus 1. There is an equation that has allowed us to solve for x. If we know the value of z, we know the value of y, we can now find the value of x. Now there are ways that we could simplify how the right hand side of that equation is written, and that's something I'm going to briefly mention in the conclusion of the video, because there are ways of writing algebraic equations that make our life a lot easier. It makes it quicker to write them and also clearer to see what's going on. But for now I wanted to keep everything very obvious, keep all of the operations that are being performed on the various different variables and numbers very obvious, so I've left everything in there. But other than that, I mean, it was pretty simple to work our way through. The only real difference with this particular example is if we've got the variable we're trying to solve for on both sides of the equation, we need to get all of those to one side, everything else to the other side, and then we find that it's no different to any other equation that we were trying to solve for. So that's all the examples that I wanted to go through. So now let's put some of those topics covered in this video to the test. So I'm going to set a series of questions for you to work through on your own. Once I've set the question, pause the video, attempt to answer it, and once you have an answer, if you get stuck, unpause the video, and I will be working through the answers here on the whiteboard. So let's start with a nice simple equation and work from there. So I'm going to bring up, let's actually start down here, we've got some room. So question 1. And I'd like you to rearrange this equation to solve for x. In other words, to get x on its own in terms of the other variables. And the equation is y is equal to z times x. So go ahead and pause, and when you come back, I will work through the answer of this question. Okay, welcome back everyone. Yes, I did say it was going to be a very, very simple question to start out with. We're going to be building in complexity as we work through some questions. It's better to start out simple and make sure you've got the fundamentals covered. So how do we get x on its own? Well, we've got to multiply. We need to get rid of that multiply, so I'm going to divide, and I'm going to divide by z to get rid of z on the right hand side. So y divided by z is equal to z times x divided by z. They both cancel, so y divided by z is equal to x, or we could obviously write this as x is equal to y divided by z. So that's the answer to question 1. So let's make things a little bit more complicated for question 2. I'm going to bring up a new layer. There we go. So question 2. So again, we're going to be rearranging to solve for x, and the equation you're going to rearrange in this question is y is equal to, open parentheses, 5 times x, close parentheses, plus 4. So go ahead and pause the video now, and when you come back, I will work through the solution to this question. Okay, welcome back. So we're trying to get x on its own. That means we need to start getting rid of some of these operations on the right hand side. And if you remember the guideline that I set, that guideline was to look for the last operation that's being applied. Well, because of our parentheses here, our last operation is going to be the addition. We evaluate the parentheses, and then we add 4 to the result of those parentheses. So how do we cancel out that addition of 4? We subtract 4 from both sides. So y minus 4 is equal to 5 multiplied by x. We'd have plus 4 minus 4, they cancel. I'm going to leave that out. So y minus 4 is equal to 5 times x. Because these parentheses no longer affect the result of the equation, even though the people who are paying attention amongst the audience will notice that they didn't actually affect the result of the equation up here in the first place, because multiply takes precedence over addition. But I added them in there just to make things a little clearer for those of you who are still getting used to all of this. So we can get rid of those parentheses. And now we need to try and isolate x again by getting rid of the last operation. The last operation is this multiply, so we're going to divide. What are we going to divide by? The 5. So y minus 4 divided by 5 equals x. So there is the solution to question 2. So let's move on to a more complicated example again. So question 3. And again we're solving for x, and in this case y is equal to, let's say, x multiplied by 9 plus z multiplied by 3 all over z. So go ahead and pause the video, and when you come back, I'm going to work through the answer of this question. Okay, welcome back everyone. So again, we're trying to solve for x. Again, we want to get this x on its own, and we can't really do anything to the numerator, the top part of our fraction or division, until we have got rid of the bottom part of the division, the denominator of our division. So the last operation that's taking place here is this division, because we see that it is being applied to the result of all of this part of the top. So we're evaluating the top and then we're dividing it by z. That means we need to get rid of that division. We're going to multiply by z. So y multiplied by z is equal to x times 9 plus z times 3 all over z multiplied by z. These two guys cancel, and that means that y multiplied by z is equal to x times 9 plus z times 3. Okay, fantastic. So we're making some progress. So again, we want to look for the last operation that's being applied. Now, it's a little tricky here. We need to recall back to our order of operations to determine the last operation being applied. We can see that we have multiplications and an addition. Multiplication takes precedence over addition. That means x times 9 gets evaluated first, z times 3 gets evaluated as well, and then the addition is applied. That means our addition is the last operation being applied to the right hand side. We want to cancel that. And which side of the addition do we want to cancel? Well, we want to get rid of anything that isn't relating to x. We're trying to get x on its own, so we're going to subtract z times 3. So y multiplied by z minus z times 3. Again, you'll notice the order of operations is such that we are subtracting z times 3 from the entirety of the left-hand side of the equation. And that is going to give us x multiplied by 9. Again, if we had plus z times 3, then minus z times 3, they cancel. That leaves x times 9 on its own. So we're making real good progress here. If you did get stuck at that point or made a mistake in that particular stage of working, it's most likely because you weren't recalling the order of operations. You need to think of our order of operations and use those rules to understand why this addition is the last operation being applied, and therefore it's this addition that we're trying to cancel. If you did make it to this stage, congratulations. Hopefully from this point, it's very easy to solve for x because we just want to divide by this 9 here. So we're going to take y multiplied by z minus z multiplied by 3. I'm going to divide all of that by 9, and that gives us x. So that is the solution for question 3. If you made it all the way through, congratulations. You're obviously picking this up very quickly. So there's one last question that I'd like to set, and there's going to be another operation introduced in this question. We're going to introduce a square. So yeah, I should have enough room here. Fantastic. So question 4. Again, I'd like you to rearrange this to solve for x, and this equation is z is equal to x multiplied by 5 plus 3 all squared. So go ahead and pause the video. When you come back, I'll work through the solution to this question. Alright, welcome back. So again, we're looking for the last operation being applied to the right hand side so we can start cancelling down and making the right hand side smaller in order to isolate x. We're trying to solve for x. So how do we cancel down the right hand side? Well, the last operation is this power of 2, it's this square, and we know that we cancel that with a square root, so we need to take the square root of both sides of the equation. Again, recall a square root can be a positive or a negative value, so I'm going to say that plus or minus the root of z is equal to x multiplied by 5 plus 3, because that cancels our square, and then we can get rid of the parentheses because they no longer affect the result of our equation. The next thing we need to do again is look to see what is the last operation being applied. You've got to be careful here. We have a multiply, we have an addition, multiplication takes precedence over addition. That means the multiplication is applied first. We evaluate x multiplied by 5, and then we add 3. That means the addition is the last operation that we have applied, and that means it's the addition that we're going to cancel, and we're going to cancel that by subtracting 3. So plus or minus root of z minus 3 is equal to x multiplied by 5. We then simply need to get rid of this 5. We get rid of the 5, it's a multiplication, so we're going to cancel it by dividing. So that means our final answer is plus or minus the root of z minus 3, all of that divided by 5 equals x. Alright, so hopefully you managed to work through all of those questions okay, and hopefully you now have a better understanding of how to rearrange equations and why rearranging equations is so important and so useful to us. If you were already familiar with rearranging these equations, perhaps this video helped refresh your memory on some of the topics, or maybe it even gave you a different way to think about rearranging equations, because my commentary during this video described very intimately what was going on in my head when I'm looking at these equations and I'm thinking about how to rearrange them. So maybe if you personally thought about it in a different way, you now can see how I think about it, and maybe your way works better for you, but maybe you find that you prefer the way that I've described in this video. So hopefully for some of you that this isn't new, for some of you that are going over this again, you now have a different way of thinking about it that you may or may not prefer using. So to recap, there are some simple rules to follow when rearranging equations. The most important rule is that we must do the same to both sides of the equation. Whatever we do to the left-hand side, we must do to the right. Whatever we do to the right-hand side, we must do to the left. You must always do the same to both sides of the equation. Our other rule was that multiplication cancels division and vice versa, addition cancels subtraction and vice versa. We've also seen during this video that square roots cancel the power of 2 and vice versa. So it's all about opposites, if you will, all about operations that cancel other operations. And we saw our simple guideline, which really is helpful in the vast majority of cases. And that guideline is to determine, using our order of operations, the last operation that is being applied to the side of the equation that we're trying to reduce down in order to isolate a variable on that side of the equation. So you identify the last operation being applied, and then you cancel out that operation. Now finally, before I conclude this video, I did want to point out that throughout this video I've always written multiplication with the times sign. Now in algebra, if you have a number multiplied by a variable, it's actually often common to just leave out the times sign. For example, if I had 5 multiplied by x, or indeed x multiplied by 5, it is most common to see this written simply as 5x. It's a lot quicker to write, it's a lot clearer to see, you don't get the multiplication and the x variable confused, so it's very common to see having numbers and variables being multiplied together simply written like so. It's also applied if you have single letter variables being multiplied together, then you can leave out the times sign there as well. For example, if you had 5 multiplied by x multiplied by y, you could simply write this as 5xy. You can see a lot shorter, a lot quicker to note. The reason I use the multiplication signs, the times signs in this video, is just so that it's very explicit, very clear as to what operations are being performed on the numbers and the variables. But you can see that there are quicker ways of writing this particular type of operation, and if you ever see equations that are using such notation as 5x or 5xy or anything like that, just remember that it's simply a shorthand way of writing a multiplication, that in actual fact you're taking 5, you're multiplying it by x, and you're multiplying it by y. I'm going to start using this shorthand in future videos. It simply is the exact same thing as this. There's no difference, it's just a shorthand notation. So I hope that everything in this video made sense. If not, perhaps watch over it again. If you're still having trouble by the time you've watched over it 1 or 2 times, then do be sure to head over to 3D Buzz, voice your questions in our forums, and even myself or one of our other knowledgeable members will be very happy to go in and help point you in the right direction and try and get you up to speed with the concepts in this video. So thanks a lot for watching, everyone.